Alright, here's the video I promised I'd send out. Sorry it's coming a little bit later than expected, but here we go.
So let's talk about the concepts of oxidation. And reduction. What? What's your question? So here's a nice little mnemonic to help you. So oxidation is when we lose electrons. It spells out Leo. Reduction is an electron gain. Or if you put reduction at the bottom, it's Ger. So what do we say? Leo, the lion, says Ger. And to illustrate that with, you might have done oil rig in freshman chemistry, but use this one, it's better. When we're talking about in terms of electrochemistry, we're talking about assigning electron states or oxidation numbers to keep track of where the electrons are going. So let's illustrate that with a couple of examples. So here's hydrogenation. And when we're looking at electron states, we're basically only applying it to one atom or a set of atoms in particular. We will say the whole molecule is either oxidized or reduced, but we base that on one element. So if we take hydrogenation with this alkene component, we'll just get butane. So let's look at these two carbons right here, or just this one on the end really. So that one is C, double bonded to C, H, H, and then the rest of that I don't care about. So looking at this carbon, we do want to look at electronegativity values. Why does that matter? Well, it tells us where the electrons are going to go. So with the hydrogen is an electronegativity of 2.1. 2.1, and carbon is 2.5. So we say that, oh, do you have a question? So we say that because it's less electronegative, we just say the hydrogen is donating one electron. So both hydrogens donate one electron each, and then the two carbons in the middle, they're both the same, so it's an equal sharing of electrons, no donating or taking it away. So this we say has -2 electrons, so its oxidation number is -2. And if we look at this, because each hydrogen donates one electron. 1 plus 1 is 2. And then we look at this one over here, so we have carbon, carbon, hydrogen, hydrogen, hydrogen. So now the only thing that's different is that we have one hydrogen on. So now instead of donating only 2 electrons, we have 3 electrons total. So that oxidation number becomes -3. And so you see right there, because it gains electrons, not as in it's mutated or whatnot, but simply because there's a less electronegative element attached to it. So this is an example of reduction. Now let's do an example of oxidation, where we take an aldehyde and we'll oxidize it up. O is common symbol for oxidize. We'll oxidize it up to a carboxylic acid. So again, let's just look at this cute little carbon right there. So it's carbon, carbon, oxygen, hydrogen. So the hydrogen again just gives one electron to it, but the oxygen with its value of 3.0, I think it's 3.0, it's going to take away 2 electrons because it's attached to 2 bonds. So it's going to be gain 1 electron, lose, oh boy. Math of electrons is hard. So it loses -2 electrons and it gains 1 electron. Yeah, it's a +1 oxidation state. Whereas if we compare it with this carbon over here, we get, that's not what I wanted to draw out. Carbon, oxygen, So in this case, we've completely eliminated the hydrogen, and we've got 3 oxygens, or 3 oxygen bonds pulling away carbon density, electron density from carbon. So that number is -3. Oh, sorry. So there you can go. There you see that because we lose electrons, it's oxidation. And so the general definition for organic reactions, if you oxidize something, you're going to gain oxygen or lose hydrogen, whereas reductions are loss in oxygen and or gain in hydrogen. So that concept is actually pretty simple. But why is this important in terms of the context of metal ions? Well, really metal complexes. Each metal on the periodic table has a specific oxidation state, depending on what else is bound to it, or just where it's sitting in the periodic table. So if we consider rhodium, let's find that on the periodic table. What? Below cobalt, yeah. So that is in group 9, so it's got 9 electrons. But the thing about transition metals is that the d orbitals come before the s orbitals. So with rhodium in the 4th group, it's got 4d electrons. We're going to fill up the 4d orbitals before we fill up the 4s2 orbitals. So the way to remember that is that you die before you survive. So well, it's just to help you remember it. So pay no. So with the 9, so we saw that rhodium has 9 electrons, so we'll just follow the Pauli exclusion principle. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and look at that. It's got 1 unshared electron just sitting right there. So rhodium is going to, actually, in its neutrally charged state, it's 0. That's its oxidation number whenever it's neutral. But this is key. Understanding this configuration is useful for understanding how to assign oxidation numbers later on. So in terms of oxidation numbers, it's really helpful to keep track of where you're at in a metal catalyst reaction. So what I want to go over is the Monsanto. I think so. Yeah, they're like the GMO gods. So this one requires methyl iodine, carbon monoxide, and water to make acetic acid. Notice that we're using carbon monoxide, which is highly reactive, and if you breathe it, it will kill you. That's the Lewis structure. Yeah. Well, very low amounts, but they decided to turn it into something useful. So for this reaction, this is not going to happen by itself. Well, it's not going to get to where we want by itself, because the carbon monoxide would simply go, woohoo, tack on, get the iodide to leave, and we'd be done. So that's why we need a catalyst to get where we need to go. So the catalyst of interest we're going to use is rhodium, which is CO, CO, I, and I. I think this has a charge on it, doesn't it? -1. Okay. So first, before we do anything else, let's just find out what the oxidation number of this rhodium ion is. So a simple way to figure this out is just to take each group off, make a basic resonance structure. So we get I minus, CO, CO. Whoops. So carbon monoxide, these are both neutral groups. So what do they contribute to the oxidation number? Nothing. However, these two iodide groups do have 2 minus charges, which indicates we're taking away 2 electrons. So since we're taking away 2 electrons, this has got to be +2. I think so, yeah. I'm gonna need to fix that. Yeah, it is +1 because we take this guy into account. All right, I'm gonna need to check my notes really quick because I don't remember how this reaction works. They're not really. The funny thing about transition metal anions is that they're not really full covalent bonds. They're just, and they're not really ionic either. They're just some mutated form in between. Yeah. Okay. So for now, I'm just going to leave off the charge just to make it easier to write on, make notes on. So the first thing that happens is, okay, here's my good leaving group, iodide. Or wait, we want that to come on, don't we? Yep, that's the first thing that happens. And I wish I had my notes with me. Well, I do, but... So rhodium is just going to pick up that, it's going to attack that methyl with its lone electrons, which we've seen that it has because of its electron configuration. So what happens in the next step is that we get 3 iodines attached to it. Now, not at first. Comes CH3. And then CO plus an iodide. floating around. So let's again look at the oxidation number of rhodium. So here it was -1. No, it was +1. It's +1 over here. But if we look at the methyl anide, or if we look at the methyl group we attached on, if we took it off again, it would be a carbanion, which is a negative charge. So that indicates that this group has to take an electron. So because it takes an electron, its oxidation number has to increase. So now we are in the +2 state. Then nothing would change. Yeah. We break it off and see what the charge is, taking or leaving electrons away. So because now we've attached rhodium, we can kind of say it's electron deficient because it likes to have 6 things attached.
There should be an arrow. See, from where we draw from the rhodium to the methyl group, we should have the iodide, or the sigma bond coming off with the iodide as well.
To it. So iodine is now going to act like our nucleophile and just swing on in there. I really don't think there will be that much of this on the test because we did not cover that this much. But it's useful to learn. So now we have rhodium. So now, since we've added another negative group onto rhodium, because if we take it off, it's just I-, it's now going to go up to +3. Now this is really the key step that's happening here, which is going to lead us to our desired product, is that this pair of electrons in the methyl group is actually going to attack that carbon monoxide. Let's just draw that out to make it a little bit more visual. Carbon monoxide could easily, well, when it's attached to the rhodium ion, or metal I mean, it's easily able to accommodate that pair of electrons coming from the methyl group. Why? Because it can just pop one of those electrons onto the oxygen and we obey the octet rule. So now what we get, and by the way, RH is a letter in the Welsh alphabet. It's more like an RH. Hra. Now, rh, it's hra. Mm-hmm.
Those pair of electrons on that methyl group, is that attacking the bond, the CO bond, or is it going onto the carbon?
It's going onto the carbon. Okay. And so now the next thing that has to happen is that, remember that we have this CO group coming, or just sitting around right here. Put a star next to it so you remember where it comes from. Oh, that was the wrong place. So that is able just to come in and attack the rhodium ion directly. So then again we get 6 things attached. Rhodium, I.
Where did the carbon monoxide just floating around?
It's just somewhere in solution. And now look at this. We're almost back to our original our original catalyst. All we have to do is get this I- and this acetate. So in order to make that happen, this pair of electrons will attack right here, the aldehyde. Now, there really is no good way to represent this. But as this pair of electrons within the carbon, oh wait, this should not be an oxygen. It's just going to attack that iodide, taking it with it. And those pair of electrons will go back onto the rhodium. So we regenerate the catalyst, I, R, H, CO, CO, and we get iodide acetate. And so one question you might have is why it doesn't go from the iodide to the carbonyl is because if we look at this compound right here, that's an acyl halide. And remember, those are super reactive because we can just add to the carbonyl, bring up the electrons to the oxygen, bring it back down, kick off the halide. If we were to add it in this red arrow direction, we get O minus, then another carbon group, and I as well. Yeah, it would just nothing would happen, and yeah, it would still be attached to rhodium. So then with this acyl halide, we use this reaction only to get to the acyl halide. What we do next with the acyl halide is just do a simple substitution reaction. So we could just do O minus, swing it in there, then swing up. So we get O minus, I, OH, bring it back down, bring it off, and voila, we have our acetate group. Our acetic acid. So remember that with acyl halides, we can just basically react them with anything. We don't need any extra catalyst once we get to it because they're super reactive. In fact, if you want to do something fun this weekend, go buy some SOCl2. It is thionyl chloride. It looks like this. That is a nearly double acyl halide. It's super reactive. So you can use it to kill somebody or give yourself cancer. So don't.
Cure this substance.
No, you can't really. I think you have to have a special license to buy those kinds of chemicals. Because like thionyl chloride is very precious for synthesizing certain things. All right.
Question.
Oh yeah.
For this rhodium catalyst, is it like a metal plate?
I think it's more like a sponge, where it's just all powdery-like. Often, what they'll have for metal catalysts, and you'll learn this in 386, is that you have just a metal with lots of little pores inside. Yeah.
When it forms like the octahedral shape with the 6 ligands, though, we assume that rhodium is like decreased, right? It's like they came up inside of one of the pores and then it came out.
Probably. You'd have a liquid solution just flow. Mm-hmm. Okay. So, do you guys want this as a recording?
All right, that's it.